All right then. In Chapter 2, we are going to move on to Essential Chemistry for Biology. So, back in Chapter 1, I talked about the various levels of organization at which you can look at things. And so, what they're doing in this book is now moving to the small scale and working our way up. So, first we'll talk about general chemistry, and then the next chapter will get into the macromolecules associated with living things. Now, in this first unit, as I said, we'll talk about these types of chemistry, and we'll also talk about cells, right? So from the ingredients for living things, we then get onto the how is our living things put together, right? So from the parts to the parts as a functioning whole in the form of cells. Now, you might say, well, why do we have to care about chemistry in here? Well, there's a few things, and they give you three examples in the beginning of the chapter. One is what you eat. Now you're saying, well, those are copper pipes. I don't eat copper pipes. True. But the copper in a pipe is the same as the copper that's in something you consume. Like if you, a lot of breakfast cereals have a little bit of everything you need each day. That's the same element of copper. And the interesting thing is that if you don't have enough copper in your diet, it can cause nerve damage, even brain damage. But too much can also harm vital organs. So with many things, you have to have just the right amount in order to remain healthy. Salt, right? We all love our salt. If you're thinking about those little grains that are being cast onto those fries there, consider this. Table salt, sodium chloride, is a combination of an explosive solid, the the sodium, and a poisonous gas, as if you think of chlorine gas. But bound together, they're this thing that we use to make food taste better. Also, how chemistry connects the entire world. We tend to think of things as being local. Uh, we'll get into this a little bit more during the semester, but the exhaust released by a car in Boston, right, the various gases that are contributing to the greenhouse effect, that will, and contributing to climate change, global warming, it actually helps lead to the death of coral in the Great Barrier Reef of Australia, the other side of the world. So we have to act locally, but we should be thinking globally. Now, radioactivity, this is something we're all familiar with at various levels. Technically, what radioactivity is the emission of high energy particles, right? So that there's substances that release particles that are moving at a high speed that have a lot of energy, and that energy can be put to use. Now, in the bad side, radioactivity can kill cells by that energy damaging DNA, and the DNA holds the codes for all the things being produced in the body. So obviously that would be a problem. But we can also use radiation for medicinally beneficial uses, like treating cancer. Right. So instead of just radiation washing over the body and all the cells getting damaged, what if you very carefully applied radiation to cells that you wanted to damage, such as cancer cells? Radiation therapy is just going to expose a small part of the body to a very precise dose of radiation. And so, if you're, some of you folks might be going into the radiology program, knowing chemistry is going to be essential to understanding biology, because how do you understand radiation? Chemistry. Also, one of the wondrous things that radiation does is we can use it to tag things. You're looking at a cross section of a person, and those red areas, those hot areas, have absorbed radioactive material that was most likely injected into the bloodstream. So you can find something in the body without having to cut it open. Right? X-rays only show you the hard stuff, but to see things in the soft tissue, used to be you had to open the person up to look inside. Well, now we have ways of doing, visual examination of the inside of a body without having to cut it open. Now let's get down to the real basics. Matter. If you take any biological system apart, eventually you wind up with a pile of chemicals. Right? You say you dissect a frog, and you have muscles and bones and the heart and liver and all that. If you took each of those parts and kept breaking them down further and further and further, eventually you have chemicals. So getting into some basic terminology here. Matter is anything that takes up space, occupies space, and has mass. There is literally stuff to it. So what is mass? Mass is the measure of the amount of material in an object. Now, don't confuse this with weight. A lot of the time people say mass and weight are the same. They're not. If you take something that weighs 100 grams, okay, on Earth it will weigh 100 grams. Weight is the force of gravity on that item that's 100 grams. If you take that same thing to the moon, it's going to weigh a lot less. It still is 100 grams of mass, but there's so much less gravity on the moon that it's not pulling on it so hard, so it would feel lighter. Right? So weight is just how much gravity is pulling on something. Typically, everything we do is going to be on planet Earth, so that's kind of consistent. But just keep in mind, mass is just measuring the amount of material in an object, even down to how much material is in an individual atom. Now, elements are substances that can't get broken down into other substances by chemical reactions. If you think of the copper pipe you saw in the beginning of the lecture, you can break down the parts of a pipe. There's usually other materials in making things like metals. But if you eventually got to a copper atom, that is an example of an element. It's something you can't break down into other stuff by chemical reactions. You can't dissolve an element into smaller units, right? So the most simple unit of any particular item is going to be the element. So all matter is made of chemical elements, right? So eventually you put all this stuff together and any object or thing around you is made of chemical parts. Now you've probably seen this at some point in time, the periodic table. Don't panic, we're not going to be memorizing the periodic table. In fact, there's only a handful of elements we really spend most of our time on. In fact, there's about 5 that we probably spend most of our time talking about. So a lot of the stuff in here we won't even mention in this course. But if you haven't really worked with one of these before, you might say, well, what is this? You've seen it before, but what is it? Well, each one of those little boxes represents an individual element. Right, so the one they've highlighted there is C, which is carbon, which is, C, which is carbon, which is obviously a critical thing. Our living things on Earth are based on carbon molecules. If you look closely at one of those boxes, you'll see up top the atomic number. That's how many protons are in an atom of carbon. The symbol of the element, so if you're writing out the names of the chemicals, instead of writing carbon, hydrogen, oxygen, blah, 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 you just write the symbols out. So it's a lot easier to describe a particular material. And then at the bottom is the atomic mass. So here's that mass term. That's the mass of an average atom of that element. So that when you look at all these little boxes, each one of them has a specific number of protons and a specific atomic mass. Now, another one that's shown in the illustration, there's a little arrow pointing to Cl, that's chlorine. If you go further down, you'll see that some of the names, some of the element symbols don't seem logical. Like if you go down, you see mercury as Hg. Well, some of these symbols come from terms that were originally Greek or Latin. So not all of them are intuitively obvious. So yeah, C for carbon, C for chlorine, Hg for mercury. So if you're looking at blood pressure, it's how much, how far up a column of mercury can get moved by the pressure within the blood vessels. So that's why you see it described as Hg in those when you're using those things. Anyway, just sort of giving you the general feel. If you're going on to the health fields or further in the sciences, you will probably be taking chemistry courses. If not, this is just going to be sort of an introduction, but you won't have to go much further in this. So again, each one of those is an element, and we're just going to be spending most of our time on a handful of them. So don't freak out that, oh my God, what is all that stuff? Don't worry. All right, so again, there's our chlorine, which is half of your table salt. There's mercury. And just giving a couple of examples of elements, again, things that can't be broken down into smaller units by chemical reactions. Now, of the 92 naturally occurring elements, some of those in that previous table only exist in the laboratory. So people cooked them up, but they don't last on their own. You can't find them in the natural world. Of the 92 naturally occurring elements, 25 are essential to people. 4 of those 25 make up about 96% of the weight of the body. Some of these are called trace elements, and these are things required in only very small amounts. The term trace refers to trace amounts, small amounts, but are still essential for life. Now, elements can get together to form compounds. And compounds are substances that have 2 or more elements in a fixed ratio, like NaCl, 1 sodium to 1 chlorine atom. Now, if you were able to sort of sift all the stuff in a human body and see it as far as how much it takes up, you have this little guy here. So if you're able to take everything and layer it out, the biggest chunk of a human body would be oxygen. That's about 65% of your body. Now, it's not pure oxygen, otherwise you'd be floating like a little balloon, but it's oxygen that's bound up in many other materials. So it is oxygen if we separate everything down to the elements. So it's not pure oxygen, it's oxygen bound up with other stuff. Next would be carbon, okay? 18.5%. So carbon and oxygen, between those two, that's a good chunk of the body right there. The next one down would be hydrogen, which is about 9.5% of the body. Down from there would be nitrogen, 3.3%. And then all of a sudden you realize that whole pile of stuff represent most of the foot there, right? Calcium, phosphorus, potassium. Think about your general, if you look at a vitamin bottle, a daily vitamin, you'll see most of these guys. Some will be, something like calcium might take up a lot of that because you need a lot of calcium because you're always taking it and losing it. But when you get down to that last little box, which is basically the part of the toes, there's those trace elements. Each one is less than 0.01% of the body, right? So that whole pile of guys are collectively less than 0.01% of the body. And you just need them in tiny amounts, but they're still critical. And that's why you see them in supplements like vitamins, because you need to make sure you get those. Now, if you eat a good balanced diet, you will get all these things. But sometimes it's good to hedge your bets and make sure that you get all these things that you need. And some of them you can kind of guess. Oh yeah, calcium, that's part of your bones, and and water, which is obviously going to be hydrogen and oxygen. That's obviously important in the body, but some of them might not seem as obvious. Okay, if you look at a container of salt, not sea salt, but regular salt, you'll see it's called iodized salt. Why is that? Well, they add iodine to it. Why do we do that? Well, if someone is deficient in iodine, they can develop a condition called goiter. And you look at this person, they have that swelling down in their neck, and that's a classic sign of an iodine deficiency. So who gets iodine in their diet naturally? Well, eating things like certain plants, seafood. There are sources of it, but some people don't get access to those foods. So it was decided a long time ago that, okay, the easiest way to make sure everybody gets enough iodine is added to something everybody uses, in this case, table salt. So that's why you see iodine in table salt, and why you really rarely see people with goiter anymore in this country. Okay, so each element, remember the 92 elements, and again, we're going to spend most of our time hanging out with 5 of them. Each element consists of one kind of atom. An atom is the smallest unit of material that still retains the properties of an element. Remember the number of protons, the mass, all that. If you dissect an atom, you're not breaking it down into other elements, but just the way an atom is put together. An atom is composed of subatomic particles. The proton is positively charged, right, and that was part of that little box in the table. An electron is negatively charged, and a neutron, you can guess, is electrically neutral. So using good old helium, because it's one of your simplest elements, you look at this here and you see, okay, 2 protons, 2 neutrons, 2 electrons. Now the protons and the neutrons together make up the nucleus. The neutrons have no charge, right? Hence neutral. Protons have a positive charge. Typically, the number of electrons are going to equal the number of protons, so that you have an even balance of positive and negative charge. So 2 protons in the nucleus, 2 electrons circling that nucleus. And often you see it depicted like a little racetrack, right? There's a little line, and the electrons are on the little line running around. It's really not like that. They don't just move in one track around the atom. They're always they're circling the atom circling the nucleus at a specific distance, but it's not just one little pathway. And so that's why sometimes you'll see a picture like a cloud, because it's going around and around and around, but not just in one little path. And so eventually those electrons are passing all around the nucleus. Now, all atoms of a particular element have the same unique number of protons, from the table earlier. That number is the atomic number. An atom's mass number is the sum of the number of protons and neutrons in the nucleus. You might say, well, what about the electrons? The electrons have so little mass, they basically don't count it. If you had an electron the size of a lifesaver, small candy, a neutron would probably be like a bowling ball, right? So just compared to the protons and neutrons, the electrons basically have no mass whatsoever. So when we talk about the mass number, we're just adding up the number of protons and neutrons. Now, isotopes have the same number of protons, right? So, because that defines the atomic number, and they behave the same in chemical reactions, but they have different numbers of neutrons. So the mass will be different, but not the atomic number, because again, that number is the same number of protons. But they're going to have different numbers of neutrons. Now, if you have a radioactive isotope, this is an isotope where the nucleus is decaying spontaneously. It's dumping those extra neutrons on its own, right? So that those neutrons exiting represent energy exiting, and that's where we get to the term radioactive. Now, we do have medical uses for radioactive materials. The example they provide in your book is talking about use in treating prostate cancer. In American men, prostate cancer is the most frequently diagnosed cancer. Now, common ways of treating it are surgery, right, to surgically remove the cells, and radiation. And studies of the effectiveness of different methods have been conducted multiple times. It's a lot of research around, obviously, understanding what forms of cancer treatment are effective. And studies of the effectiveness of surgery and external radiation, right, so aiming something at that part of the body and sending a beam of energy to that tissue, are kind of problematic, because the groups of patients are not controlled for all characteristics. If you think about it, you go back to a controlled experiment, right? You're going to have those that do not receive the treatment. And it would be unethical to say, okay, we're going to take this group of people, and some people will get the treatment and some people are not going to get treated. Because if you know the individual's cancer, you have this thing that's progressing. So it tends to be looking at the effectiveness of treating everybody. So you're not going to be seeing a control in the next illustration. And if you look at the person's hand, and I've got a bigger picture coming up in a second, those little tiny things on that person's hand are radioactive seeds. So instead of aiming a beam at the tissue at whatever intervals, they can implant those tiny seeds right around the tumor. So they're giving a continuous dose of radiation, but by being placed so close to the tumor, it's just going to be affecting the tumor for the most part. So if you look at the middle illustration, the prostate, I can't point this out easily. I don't think this arrow is going to show. But if you look north of the blue tissue from the penis, you see this little round structure with what looks like a letter Y inside. Right, that's the prostate tumor. And they can do is insert those tiny little seeds right there, so it's not going to have as much effect elsewhere in the body. I'm going to do is click ahead to the chart showing the results. Now again, there's no control here. It's basically this population of patients, and you're just you're observing which treatments had the best outcomes. So if you look to the 3 bars on the left-hand side, you're seeing a comparison of seeds in gray, surgery in orange, and external radiation in blue. All right, so after five years after treatment, they're kind of all pretty similar, right? You have pretty similar, outcomes as far as number of patients whose cancer did not progress further, right? So it's basically stopped, from growing. But then look at the 3 bars that are on the right side. 10 years after treatment. Now you see a difference. And apparently the seeds are better at stopping cancer over the long term than surgery or using just external radiation. So it's kind of neat that this is a way that you can actually look at how research works. Again, with human studies, you're not going to be doing things like, this particular type of study, you're not going to use control because, again, it would be unethical to withhold the treatment. So you just see which outcomes are better than others. Now, when you talk about chemical reactions, the only players in a chemical reaction are the electrons. Because think about it, if you have 2 atoms next to each other, what's going to come into contact first will be the electrons that are circling the nucleus of each of those atoms. So only electrons are directly interacting in a chemical reaction. Now, the number of electrons that an atom has tells you the chemical properties of that atom. Chemical reactions enable atoms to transfer or share electrons, right? So when 2 atoms, are coming into interacting with each other, either somebody's going to steal someone else's electrons or lose electrons to someone else, or they share them. And we'll talk about those 2 types of interactions because they have specific names in a moment. These interactions, either transferring electrons or sharing electrons, usually results in the atoms staying close together. And what's holding them together is an attraction called a chemical bond. Now, if an atom loses or gains electrons, now you're gonna lose that equal proportion of electrons to protons. So if an atom or a molecule, the electrons are taken away from atoms or a molecule containing atoms, if they're going to be gaining or losing electrons, we call them ions. So whether they gain or lose, we call it an ion. A positive ion has lost electrons, right? Because now it has more positive parts than negative parts. If something gains electrons, it's going to be negatively charged because now it has more electrons than the number of protons in its nucleus. So ionic bonds tend to form between oppositely charged ions, right? Because you're going to have a positive and a negative, opposites attract, and that's going to have these guys hanging out together because now you've got one that's positively charged, one that's negatively charged. They'll be attracted to each other, and so now these materials, materials are going to be hanging close to each other. So compounds like table salt that get held together by ionic bonds are called ionic compounds.
Sometimes atoms complete their outer shells by stealing or giving away electrons. This happens between sodium and chlorine atoms. An electron moves from the sodium atom to the chlorine atom. The outer shells of both atoms are now complete, containing 8 electrons. The chlorine atom now has 18 electrons but only 17 protons. Because an electron has a negative charge, the chlorine atom now has a net negative charge. Such a charged atom or molecule is called an ion. In this case, a negative ion. The sodium atom has lost an electron, leaving it with an extra proton, which has a positive charge. The sodium atom has become a positive ion. Ions with opposite charges are attracted to each other, forming an ionic bond. These ions combine to form a compound with new properties. In this case, sodium chloride, ordinary table salt, is formed.
Okay, so here's a still picture of that thing that was animated. So again, when you change the proportion of electron to proton, you create an ion. Whether it's positive or negative depends on whether it has gained or lost electrons. And this is just another illustration of the same thing, where you're seeing that the sodium is lost to the chlorine. There's only so many electrons that can get held in a layer around the atom. And these atoms having a lot of electrons, you can see that they form rings. Well, only so many atoms, so many electrons can remain in a ring. So the innermost ring, you can only have up to 2. The next one out, so once you fill a ring, now you have a ring outside of that. The next ring out, you see 2, 4, 6, 8. Right? So that electron shell, that layer, can hold up to 8 electrons circling around the nucleus. Once that is full, then you have another ring to the outside. And this is where there's going to be fewer than 8. So this will be the outermost ring. It'll be the incomplete one. And in this case, chlorine has got, in the outermost shell, has got 7 out of a possible 8. So when you see that sort of condition, you've got something that's greedy for electrons. If you think of them like people, they're happiest when they have a full outermost shell. So this guy is so close to having a full outermost shell, right? It just needs that one electron. So it's going to be really greedy to grab an electron. On the other hand, looking at the sodium, it only has 1 electron in the outermost shell. So the easiest way for it to get to a full outermost shell is to get rid of that one, and now the next one is full. So often the reactivity comes down to things like how many electrons are in the outermost shell. So again, we have our sodium, our chlorine, forming an ionic bond. You have sodium chloride, right? So this is a compound, things with a fixed ratio. Now, sometimes someone isn't stealing or someone isn't getting, they're sharing, right? This is called a covalent bond. And this forms when 2 atoms share 1 or more pairs of electrons. And covalent bonds are much stronger, right? You can dissolve table salt in water. Right? It's easy to break down a lot of ionic bonds. Covalent bonds are the strongest of the bonds, and they hold atoms together in a molecule.
A covalent bond is the sharing of a pair of outer shell electrons by 2 atoms. For example, each of these hydrogen atoms has 1 electron in its outer shell, but needs 2 electrons to complete its outer shell. If the two hydrogen atoms share electrons, they can both complete their outer shells. The shared pair of electrons constitutes a covalent bond, shown in shorthand as a line. The covalently bonded hydrogen atoms form a molecule of hydrogen gas. A molecule is defined as 2 or more atoms held together by covalent bonds. An oxygen atom needs 2 electrons to complete its outer shell. 2 oxygen atoms can share 2 pairs of electrons. A molecule of oxygen gas is held together by a double covalent bond, 2 shared pairs of electrons. A carbon atom needs 4 electrons to complete its outer shell. It can share electrons with 4 hydrogen atoms, forming a methane molecule containing 4 single covalent bonds. Methane is a compound, a substance formed by the combination of 2 or more elements. We call methane natural gas. It is the fuel burned in gas stoves and furnaces. An oxygen atom needs 2 additional electrons to fill its outer shell. Thus it can form 2 single covalent bonds. An oxygen atom can share electrons with 2 hydrogen atoms, forming a molecule of water containing 2 single covalent bonds.
And we'll talk about why they are oddly arranged in a moment. So moving on to the diagrams. Now there's various ways you can visually represent a molecule. The one on the left is sort of the most detailed in terms of seeing, the electron configuration. You just see a solid line for a full layer. So you see the inner circles just are plain circles. That's because you know that they're full. But where you have the bonds taking place, now you can see the little dots representing the electrons. You can represent that same pattern in what's called a structural formula, right? Where you draw the symbols of the elements and lines representing the number of shared bonds. The others, the last two are sort of visual, I call the artistic renditions, where the electron shell is shaded in, right? So the electron shell of the oxygen and the carbon and the hydrogens. Ball and stick model is something you might have done at some point in school, where you stick together, you literally make molecules by holding little balls together with sticks. So again, all these represent the same thing. These all represent formaldehyde, which is C, carbon, H2, 2 hydrogens, O, oxygen. Now, a molecule of water, as you saw in that animation, consists of 2 hydrogen atoms joined to 1 oxygen atom by covalent bonds. But the electrons are not shared equally between the oxygen and hydrogen atoms, right? Maybe as a kid you were supposed to share a toy with a sibling, and one sibling got a little bit more sharing time than the other. It's kind of like that. Water is what's called a polar molecule. If they were all in a nice straight little line where they'd be sharing the electrons equally, it would be neutral. But because it's a single thing, and the oxygen is sort of hogging the electrons, it's weakly positive in charge. Because the hydrogens are not having the electrons as much as the oxygen is, then they are going to be weakly negative. So the fact that water, the molecule itself is polar, so we're not talking about 2 ions, the actual molecule is itself polar. Because of that, you wind up with weak electrical attractions called hydrogen bonds between neighboring water molecules. Think about how great water is when it comes to sticking to itself. Well, this is why. So if you look at these guys here, you can see that the hydrogen end is weakly positive and the oxygen end is weakly negative. So that means they're going to be all attracted to each other's positives to negatives. And that means that water is really good at sticking to itself, because they're not being held together by a covalent bond, they're being held together by these charges.
The atoms that make up a water molecule are in a constant tug-of-war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
Okay. Now, in the slides, you'll see these checkpoints. Sometimes they have these little questions that are sort of ways that make you go back and sort of refresh a term that you've heard earlier. So in this case, when you see molecules being formed and the partners in those molecules are charged, right? So you have a lithium with a positive charge and a bromide ion with a negative charge. If you see charged elements joined together, right, these are called ions. This would be an ionic bond. So just a sort of a quick refresher there. Now, cells, living things, are constantly rearranging molecules. Right? They're taking molecules and breaking them apart, putting other molecules together. Changes in the chemical composition of matter are called chemical reactions. And a chemical reaction includes the reactants, the starting materials, and the products, the end materials. Think of it like a recipe, right? If you want to make a cake, you get the flour and the sugar and the yeast and all this stuff. Those are the reactants. And then you mix them together and you apply heat, and you wind up with the product, which is the cake. Right? So reactants are the starting materials and products are the end materials. Now, chemical reactions can rearrange matter, right? They can change who's attached to whom, but they can't create matter or destroy matter. Right? Matter is matter. Matter is consistent. Matter doesn't get, doesn't decay. It doesn't wear away. It just all is getting rearranged over and over again. So a carbon dioxide molecule that a Tyrannosaurus rex breathed out, that carbon could be in a cell in your body, because that carbon, just keeps getting moved to other, through reactions, keeps getting attached to other things and has passed through the millennia being, involved with chemical reactions. And so any one of those carbon atoms from something from way back when, it could be a part of your body today. Now they tell you in the next one to predict the formula for the compound that results when a molecule of sulfur trioxide, 3 oxygens, combines with a molecule of water to produce a single molecule of product. What they want you to do here, and if you've had chemistry before, you've already done this, essentially they want you to do is predict writing that thing out, including all the parts, right? So you put those two things together. So you wouldn't have SO3H2O. Right? You're going to do is you're going to combine all the individuals of a particular element together. So it'd be, instead of SO3H2O, you'd have SO, and so 3 plus 2, and 3 plus 1 would be 4. Hydrogens, right? There's 2 of those. So it would be a single molecule product, but you only write each element once. Again, we're not going to be really doing stuff like this. It's just to understand when you see things getting put together, all of a sudden a single unit, everything's all piled up together by element. Now, cells constantly rearrange molecules by breaking existing chemical bonds and forming new ones. And so something you'll also see in these slides is what major theme is illustrated by this action. Right? When we talk about chemical bonds forming and breaking, which of these 5 things would you apply this to? And that's pretty easily pathways that transform energy and matter. Now, water is a big deal when you talk about biology. It's one of the reasons why we're never interested in whether we can live on another planet or if life is on another planet. One of the first things we look for is water. Because if it's put together like we are, there's going to be water involved. And so it's a nice evidence that something can live there or something has lived there. Life on Earth began in the water. The Earth was initially just great big oceans. So life on Earth first developed in the water, and before living things moved on to land, it stayed there for 3 billion years. Right? So life on Earth has always been aquatic. Even when things moved on to the land, they keep the water in their bodies, right? So they still have a lot of water in them, even once they're on land. So modern life is still tied to water, even today. Your cells are composed of 70 to 95% water. In fact, there was a great scene in a Star Trek The Next Generation episode where this energy being referred to humans as ugly bags of mostly water, which I guess is a way of looking at it. But yeah, we are mostly water. All the other stuff in our cells are much, much, smaller amounts of material. That's why oxygen was such a large part of the percentage of the human body. Okay, so the abundance of water is a major reason why Earth is habitable. The polarity of water molecules and those hydrogen bonds they talked about explain a lot of why water is unique and why it supports life so well. If you think about it, if you see most scenes of the natural world, you see water in one form or another. You have ice on the glaciers, you have some snow in the trees, you've got liquid water inside that, I'm guessing, a lake. You can see snow and ice on the pilings. So we see water in many different forms around us. Now, again, water molecules stick together because of hydrogen bonding. That tendency of molecules of the same kind to stick together is called cohesion. Right? So co meaning same, hesion referring to attaching. So similar things attaching to each other, we call this cohesion. And it's much stronger for water than most other liquids because of those hydrogen bonds. Because again, each hydrogen bond is weak, but there's so many of them. So think about a single thread, the strength of that versus if you wind hundreds of threads together and you form a rope, right? That rope is very strong, even though each individual thread may not be. Well, water is really good at sticking to itself. So we refer to this as cohesion. And if you've ever looked at a tree and you see these leaves on the tree, realize that water has to get from the ground to those leaves way up high in the tree, but you don't see a heart in a tree. It doesn't have a pump. How does that water get from the soil all the way up there to the leaves? Well, trees rely on cohesion to get this done. And I'll have an illustration in a second that'll talk about this. Another example is surface tension. How hard it is to stretch or break the surface of a liquid. Right, so there's little organisms that can actually run on the surface of water because they spread their weight out a lot. So they literally don't put enough pressure on the surface of the water to break through and sink in. So hydrogen bonds give water unusually high surface tension. So looking at these next couple of illustrations.
How does water get from the roots of a tree to its leaves? The evaporation of water from leaves moves water molecules up from the roots. The evaporation exerts a pull that is relayed downward along a string of water molecules from leaf to root. Hydrogen bonds cause water molecules to stick together, a phenomenon called cohesion. As each water molecule evaporates, it pulls on the next water molecule, and it pulls on the next. This relays the pull of evaporating water molecules all the way down to the roots. The cohesion of water helps to keep gravity from pulling the water molecules back down.
It's a similar principle to if you drink water through a straw, right? As the water's entering your mouth, it's attached to all the, collectively to all the other molecules, and so it just keeps feeding up into your mouth as you apply pressure. So it's kind of neat, and you might say, well, what's the pressure? If you're drinking from a straw, you're generating the pressure. Water evaporating from the leaves of the trees is, in essence, similar to your mouth drawing on a straw. So the water is leaving by evaporation, and it keeps being replaced by the water molecules that are attached to the ones that are evaporating and leaving. Hopefully we'll get a little chance to talk about this in more detail later in the course when we talk about how plants work. And you can see plants have actual cells that are modified into tubes for carrying water. And again, there's that cohesion between water molecules. Here's an example of surface tension. This is a type of spider that can literally run on the surface of water because he spread his weight out. All those long legs, there's no large amount of weight in one spot. And so it can maintain its mass spread out enough that it won't actually punch through the surface of the water. Now, because of the hydrogen bonding, water has a stronger resistance to temperature change than most other substances. Because heat is first used to break hydrogen bonds, and all those hydrogen bonds together are very, very strong, water is going to absorb a lot of heat while it's going to absorb a lot of heat while only warming up a few degrees. Right, because that heat is going to be breaking hydrogen bonds first. You've got a zillion hydrogen bonds. It's going to take a lot of heat to break them apart. And eventually, if you apply enough heat, you break them apart, and the water, leaves as steam. All right, so when you boil water and you see the steam rising up, you've applied enough heat to break apart all those hydrogen bonds that were holding together all those water molecules. On the flip side, as water cools, hydrogen bonds will form that releases heat. So evaporative cooling occurs when a substance evaporates and the surface of the liquid remaining behind cools down because heat is leaving because that energy is breaking apart the hydrogen bonds. So as that liquid leaves as evaporated water, right, it's removing heat from the whole system. So when you see, if you've ever watched a football game in the cold weather, and you can actually see steam, it looks like steam coming off a person's head. The person is sweating to get heat out of their body. The fact that the water is evaporating off their skin is how the person gets cool, because the evaporation is taking the heat off of the body. Now, if you cool off water molecules enough, they move apart, forming ice. Because if you think about it, most things that are solid are going to be denser than something that's liquid. A chunk of ice floats, right? So ice floats in water. Why? Because it's less dense than the liquid water in which it's floating. Because of that, floating ice forms an insulating blanket over liquid water, allowing life to survive under the frozen surface. If not, if you think about it, things like ponds and lakes and even the oceans would freeze, from the bottom up, freezing solid, and that would not do well for anything that was living in that water. So why is it less dense? Well, liquid water, those hydrogen bonds are constantly breaking and reforming, right? Fraction of a second, length of time on those bonds. Once you start cooling water down enough, those hydrogen bonds become more stable. And as they become more stable, it's like standing with your arms stretched out. They're going to hold molecules apart. Now you can see that there's a lot fewer molecules in that little circle than there were in the circle on the left. So because there's fewer molecules in that area, that means that it's less dense, and that's why ice will float. So good news for everything that lives in the cold parts of the ocean. Now, water is going to be a part of most of the reactions we're going to be talking about, right? A liquid consisting of a homogeneous, blended mixture of two or more substances is called a solution. The thing that's dissolving stuff in the solution is called a solvent. The stuff getting dissolved is the solute. When water is the solvent, the result is an aqueous solution, right? A solution that is based by the dissolving agent being water. So going back to, talking about salt again, if you put salt in water, right, and stir it, you see the crystals go away. What's happening? Well, those nice negative chloride ions are being attracted to by the hydrogen ends of all those water molecules. The sodium ion, which has got a positive charge, is getting attracted to all those oxygen ends of those water molecules. And this tugging of the water on the parts of the salt crystals breaks them apart. Right, so that the table salt is going to dissolve in water. Now, if you got rid of all the water, you boiled it away or let it evaporate, what would you see? You'd see those salt crystals back in the as a solid again once the water is no longer pulling apart those parts. So, aqueous solutions we'll be talking about. If you are looking at that salt water situation, water is the solvent, the crystals of salt are the solutes. And when you have that salt water, as a result, that would be an aqueous solution. Okay, I'm just going to pop over this. Acids, bases, and pH. Now, we're going to talk about this, and acidity does play a part in some of the things we talk about, but you won't be calculating pH, so we'll talk about these terms in sort of a broad sense, but don't worry about having to calculate pH of materials. Okay, so what are the players in this one? A chemical compound that releases hydrogen ions, right, the little positive hydrogen ions, to a solution is called an acid. So if you put something in a solution and it dumps hydrogen ions, we call that an acid. If you put something in a solution and it pulls hydrogen ions out of solution, right, and binds them to itself, it's accepting hydrogen ions, and doing so pulls them out of the solution, we call that a base. So to describe how acid a solution is, chemists use the pH scale. And this is a measure of the hydrogen ion concentration in a solution. So if something is dumping lots of hydrogen ions into a solution, it's going to be acidic. If it's pulling hydrogen ions out of a solution, then it's going to be basic. And in many chemical and living systems, things like buffers exist that minimize changes in pH. So if you take a solution and you add an acid, instead of the pH, dropping like a rock, okay, this will sort of absorb some of those hydrogen ions, right? So they're not all released into solution. It's like, hey, some of you guys come over here, right? And it keeps the pH from changing massively. Same thing with a base. If you put a strong base into a solution, and it'd be sucking all the hydrogen ions, it'd be like, hey, add some hydrogen ions back to the solution, right? So it's keeping changes in pH from being rapid and massive. So the pH scale, and you've probably seen all these at some point or another. Now, right in the middle, neutral, where the proportion of hydrogen to hydroxide there is equal, so that's neutral. You don't have a lot more hydrogen ions, or you don't have a lot fewer hydrogen ions, right? So it's equal proportion. We call that neutral pH. And the scale, when we talk about the numbers, it's representing that proportion. Now, unlike pretty much everything else, you'll always hear me saying, don't forget the units, right? Is it milliliter, liter, gram, whatever. This is one of the few examples of something where there's really no units. You're going to say the pH is 7, not 7 somethings. It's just 7. It's basically describing that proportion. So this is one of the few times where you just use the number in an answer and not add any units to it. So neutral is pH 7. Pure water, if I boiled water, collected the steam, made distilled water, that would be pH 7. Human blood is a little bit above 7, so human blood is relatively neutral. Urine is a little more acidic, okay, so there's more hydrogen ions in that than there are in human blood. Seawater is actually pretty similar to human blood. The fact that all life began in the ocean, probably this is a remaining element of that, because we sort of have seawater in our blood, if you think about it that way. Now, as we go in either direction, higher pH, the number's getting higher, lower pH, the number's getting smaller. We're seeing extremes in pH. Now, if we go down, right, pH getting lower and lower, the number's getting smaller and smaller, this is something that's becoming increasingly more and more acidic, which means what's something that's acid? Something that gives up hydrogen ions. So as that pH number gets smaller and smaller, it means you have more and more hydrogen ions being lost into that solution. Anything that's really extreme from neutral is generally not friendly to life. Some of you folks may already work in medical fields. If you're testing the pH of someone's blood, if you start getting anything like 6 or 8, you've got a situation that may be incompatible with life. Because you might say, well, 6 to 7 is not a big difference. Keep in mind, each number, so say going from 7 to 6, it's not linear. If you're going from 7 to 6, it isn't that there's one more, amount of pH. It's 10 times more hydrogen ions. So from 7 to 6 is going to be a tenfold change, tenfold in this case increase in the hydrogen ion concentration. 7 to 5 is going to be 10 to 6, 10 to 5, 100 times higher concentration of hydrogen ions. So when you see these changes in pH, each one of those numbers represents a big change. It's kind of like when you hear about earthquakes, and they talk about a 5 or a 4 or whatever. Each one of those number changes is a tenfold change. Same thing with pH. So the number differences may not seem big, but remember, each one of those is a 10 times. So 7 to 6 is 10, 7 to 5 is 100, 7 to 4 is 10 times 100, 1,000, right? So it's big changes. And again, you look at the things that are in the extreme of acidity, right? All right, some of the are things we consume, but when you get way down there, you're talking about things like battery acid, right? Things where you see a skull and crossbones on a label, because something like that, battery acid is sending so many hydrogen ions into solution, that it can mess with the existing chemicals in your body. Let's go in the other direction. Let's start from neutral at 7 and go to the higher numbers. The higher the pH, the lower the hydrogen concentration, because bases are what? Pulling hydrogens out of solution. So again, hanging out in the middle, it's like, yeah, that's neutral. But you go up to milk of magnesia. Why is it you take milk of magnesia? Because your stomach is uncomfortably acidic. Well, if you have too many hydrogen ions and you're feeling uncomfortable because of that, you put in something that's what? Going to absorb those hydrogen ions. So that's why we take milk of magnesia with regard to an acidic feeling stomach. But once we start getting past there, we get into stronger and stronger bases. And again, you start seeing things that you typically see labeled with a skull and crossbones because they will injure living materials. And right about now, we're all using a lot of bleach, right? Because we're trying to do is destroy things like virus particles. So a very strong base is one way in which you can deactivate a virus or kill a cell. And you get up to oven cleaner. If you've ever had the joy of cleaning an oven, it's that stuff that's hard to get rid of. Well, what is that hard to get rid of stuff? Greases, oils, lipids, proteins, right? So these are all organic molecules that are really stuck on there. So you use a really, really strong base, and it's going to break them down, right? So it can break down even tough, stuck-on grease in an oven. If it can do that to grease in an oven, it can really mess up soft living tissues like the ones in your body. So extremes of pH are generally not friendly to life. And this next illustration just sort of gives you another way of looking at the pH scale. So again, the proportion of hydrogen to hydroxyl ions here, if there are relatively few free hydrogens, that's basic, because the hydrogens have been getting pulled out of solution. If there's more hydrogen ions, then that would be an acidic solution because hydrogen ions are being released to solution. Now, you might say, okay, so I understand how my stomach works now, but there's larger scale changes in pH in the world. I mentioned earlier about the exhaust in Boston harming the corals out in the barrier reef. That's because one of the parts of auto exhaust is carbon dioxide. Carbon dioxide can dissolve, be absorbed into water. If you ever leave a glass of water next to, by your bed at night, and you drink it in the morning, it tastes a little funny, that's because overnight that water was absorbing carbon dioxide from the air, and you have a really, 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 really weak carbonic acid solution, right? It's become slightly acidic, and that's why the taste is kind of funny. So take this out to an ocean. So all the carbon dioxide we're dumping in the air, as that gets absorbed by the water of the ocean, you wind up with the ocean becoming acidified. The ocean becomes more acidic. And something like a coral, which is made of calcium, if you have corals living in an acidic solution, that acid is going to start breaking down those little shells. And that's why it's become a risk. Climate change has become a risk to corals, because it's warming the water, which causes some problems with its physiology, but it also literally is breaking down the little carbon shells because it's becoming more and more acidic. Okay, so I'm going to just skip over this. All right, so evolution connection. So last major point. Radioactive decay can get used not to observe important data about the history of life on Earth, right? Some things have been alive a very long time ago. We can find remains of them today. One way you can get an idea of how old something is by taking fossils and measuring the ratio of two isotopes to learn how many half-life reductions have occurred since it died. Right? So living, there's an amount of isotopes in the living thing. Once it dies, it's not going to be making more isotopes, right? Because it's dead. It's not chemically reacting anymore. Over time, those isotopes will naturally break down. And we actually know how long it takes for 100% of something to break down to 50%. For 50% to break down in half to 25%, 25% in half to 12.5%, etc. We call those half-lives, how long it takes for something to go from a number to half of that number, right? Half of the life of that isotope. So looking at something here, we have a little mouse which during its life is chock full of carbon-14, right? It's a type of carbon that has a little more neutrons than carbon-12. Well, once that mouse dies, okay, that carbon-14 is going to degrade into carbon-12, right? So if you look at the bar on the left here, let me pop over to the bigger picture here. If you look at that bar on the left, okay, at the time of death, it's 100% carbon-14, no carbon-12. Because that's, when it was alive, it had all carbon-14, no carbon-12. So if you know how much carbon-14 relative to carbon-12 is in that mouse when you find it thousands of years later, you can guess how long it's been dead. So let's take this over here. So at death, it was 100% carbon-14. The amount of time it takes to get to 50% of the carbon being carbon-14 and the other 50% being carbon-12, well, that's 5.7 thousand years, 5,700 years. Okay, so to get to half of that takes another 5.7 thousand years, another 5,700 years. So from 100% to 50 is 5.7 thousand years. The next half, to get it down to 25%, now you're all the way out to 11.4 thousand years. To go from 25% to 12.5%, that's another 5.7, so now you're out to 17.1, right? So as the proportion changes from carbon-14 to carbon-12, as you get more and more carbon-12, that tells you how long this thing has been dead, how long it's not been, undergoing metabolism. So if you take that mouse and you measure the proportion of carbon-14 to carbon-12 from that fossil, you can get a rough estimate of how long. If there's only 25% carbon-14 to 75% carbon-12, then it's probably been dead for about 11.4 thousand years, or 11,400 years. So you're not going to get like an exact date, but it gives you a rough idea of how long something has been dead. And that is the end of the chapter. So when we next meet, we'll move on to chapter 3, talking about organic molecules.